Hi, I'm Young-Sen from Purdue University. In this talk, I would like to introduce our work, the maximum binary tree problem. This is joint work with Karthik, Alina, Gabriel, Shubhang, and Minshen. In this talk, I will start with an introduction, followed by our two main results. First, the inapproximability result, and second, the fixed parameter tractability result. So let's consider a network optimization problem in the following form. Our goal is to find an optimal subgraph with specific properties satisfying degree constraints. So one example will be finding a minimum spanning tree with degree constraints for each vertex. And another example will be finding the smallest subset of vertices in a graph so that in the subgraph induced by these vertices, the minimum degree is at least d for each vertex. One can maybe think of flipping the objective and the constraint. So an example will be finding among all the possible spanning trees, the one that minimizes the max degree. Well, these problems, they're mostly hard, thus they have led to interesting techniques in approximation algorithms. And in this talk, we're interested in a maximization problem. That is finding a maximum binary tree in a given graph. So a binary tree in an undirected graph is a subgraph that is connected and acyclic, where the degree of each vertex in the subgraph is at most 3. While a binary tree in a directed graph is a connected and acyclic subgraph, where for each vertex in the subgraph, the out degree is at most 1 and the in degree is at most 2. One may want to specify that the binary tree is rooted at a specific vertex. So in an undirected graph, we say that the root has to satisfy the constraint of degree not being greater than 2. While in directed graphs, the out degree of the root is exactly 0. So let me show you an example of a directed binary tree. Suppose we're given this instance of directed graph. Then a possible binary tree can be the subgraph formed by the red edges. And we can observe that for each vertex in this subgraph, the in degree is at most 2 and the out degree is bounded by 1. And the root is the rightmost vertex that does not have any outgoing edges. So the problem of interest is finding the maximum binary tree in a given graph. So we term the problem of finding the maximum binary tree in undirected graph, undirected MBT. Also, one may be interested in the rooted version, where the input is given not only the graph but also a specific root. If the given graph is a general directed graph or a directed acyclic graph or DAG, then we term this problem directed MBT or DAG MBT. Similarly, we can define the rooted version of these problems. And the goal is to find the max size tree in a given graph. So here I want to remark that the DAG MBT and rooted DAG MBT they can be reduced to each other in polynomial time. While the equivalence for other problems, it's not clear. To reduce DAG MBT to rooted DAG MBT, one can just enumerate through all the vertices as a candidate of the root. For the other direction, that is reducing rooted DAG MBT to DAG MBT, suppose we're given the root as the input. What we can do is to remove all the outgoing edges from the root and remove all the vertices that cannot reach the root. Our problem is motivated by two problems. First, it's the longest path problem. So MBT can be viewed as a variant of the longest path problem. Consider the following reformulation for longest path. The goal is to find a maximum size tree in which every vertex has degree at most 2 if the given graph is undirected. For directed graphs, the goal is to find a max size tree where every vertex has in and out degree at most 1, and the root has out degree exactly 0. So the following example kind of brings out the connection between these two problems. So the picture on top is the longest path of size 6, while at the bottom is a binary tree of size 6. The second motivation is the connection to sequence heapability. We say that a sequence is heapable if the entry can be inserted into a binary min heap sequentially and in order. So this problem was first introduced by Byers et al. And this problem can be viewed as a variant of the longest increasing subsequence problem. So we come up with an observation that given a sequence, we construct a corresponding DAG so that there is a one-to-one correspondence between an increasing subsequence and the longest path in the graph. Similarly, we also obtain the observation that a heapable subsequence has a one-to-one correspondence to a binary tree in the graph. A hardness result can be summarized by a table. What we're looking for is a maximization problem, so we say that an approximate solution is an alpha approximation if it is at least alpha times the optimum, where alpha is a value between 0 and 1. We consider 3 families and 2 assumptions. The families are DAGs, general directed graphs, and undirected graphs. Well, the assumption is either P is not NP or the exponential time hypothesis. It is well known that the longest path problem for DAGs is polynomial time solvable by a simple traversal according to a topological ordering. However, for DAGs, the MBT problem is actually hard. Assuming P is not NP, we prove that there is no polynomial time constant factor approximation. And assuming ETH, we show that there is no polynomial time sub-polynomial approximation. And there is no quasi-polynomial time, another sub-polynomial function approximation, where the function is slightly better than the one above. For directed graphs, the longest path problem is proved to be hard, assuming P is not NP. It is hard to approximate in polynomial time with a factor of nearly 1 over n. While our results for directed graphs, it's directly obtained by the results for DAGs. For undirected graphs, the longest path problem, it's shown not having a polynomial time constant factor approximation, assuming P is not NP. Assuming ETH, there's no quasi-polynomial time sub-polynomial approximation. And we have some similar result, except that assuming ETH, the hardness for the approximation factor is not as large. In this talk, what I will be focusing on is the max binary tree problem for DAGs. Our algorithmic result is a fixed parameter tractability result, parameterized on the size of the solution. Consider the problem k-binary tree where the input is a directed graph, an integer k. The goal is to answer yes if the graph contains a binary tree of size k, and answer no otherwise. Here we make 2 remarks. First, the search variant and the decision variant, they are polynomial time reducible to each other. It is clear why we can use the search version to solve the decision version. For the other direction, suppose we want to solve the decision version by the search version. What we can do is to iteratively remove one vertex after another. And eventually, by some recursive procedure, we can find a solution. The other remark that we want to make is that the undirected version of k-binary tree can be polynomial time reduced to the directed version. This is because suppose we're given an undirected instance. If there's an edge between two vertices, we can replace that edge by two anti-parallel edges. The main theorem that we want to show is the existence of a randomized algorithm for k-binary tree with one-sided arrow, and the running time is 2 to the k times poly n. So let's start with our inapproximability result. So one of our main theorems is there is no polynomial time constant factor approximation for DAG MBT and undirected MBT unless P is MP. So in this talk, what I will be focusing on is the hardness of DAG MBT. And we recall that DAG MBT and rooted DAG MBT, they can be polynomial time reduced to each other. So it suffices to focus on the hardness for rooted DAG MBT. So the hardness proof consists of two steps. First, we show that if there is a polynomial time constant factor approximation for rooted DAG MBT, then there's a p-test for this problem. And this argument follows by a self-improving reduction, which amplifies the approximation factor. While the second ingredient of the proof is the APX hardness of rooted DAG MBT. By combining these two, we can show that assuming P is not MP, there is no polynomial time constant factor approximation. So the self-improving idea is due to Karger, Motwani, and Ramkumar when they're trying to show the hardness for longest path. And we note that the hardness for the undirected problem can be proved in a similar fashion. Okay, so let's try to focus on the first step of the proof. So let opt of G denote the number of vertices in the MBT of the given graph G. Suppose we already have in a black box manner an alpha approximation algorithm A for this problem. What we want to do is first construct a squared graph G squared based on G and run the black box algorithm A and get an alpha approximate solution T2. The goal is to recover a solution T1 for the original graph G by examining T2. And by roughly applying the inequality relation shown below, we can show that the size of T1 is at least square root of alpha of the optimum. Thus, we amplify the approximation ratio from alpha to square root of alpha. So later on, the goal will be showing the leftmost and the rightmost inequality, while the middle inequality is implied just by definition. So we remark that by squaring the graph roughly t times, where t is a function of two given constants, alpha and epsilon, then we can have a 1 minus epsilon approximation. And the running time is polynomial in the number of vertices to the sum function of t. So this is okay because we're focusing on a p-test, not an f-p-test. The square graph construction is described as follows. Suppose we're given the graph G. What we're going to do is to first add a source to the graph and connect the source to each vertex. Then from the original graph, we replace each vertex by a copy of G prime and assign the edges according to E. So we added 3 edges between the copies. An example will be the edge from the V1 vertex of the V1 copy to the source vertex of the root copy. and the other two edges, they're defined in a similar way. Eventually, we specify the root of the root as the root of g squared. So let's go back to the inequality relation that we want to show. For the rightmost inequality, it's shown by the following lemma. So in this lemma, suppose we're given an optimal solution T of the original graph G. What we can do is to find another solution for the square graph G squared by just taking the vertex by just examining the vertex copy where the vertex is involved in the solution T. And for each copy, we replace we plug in a solution which is T plus an extra source. So eventually, the solution T squared of the squared graph has size at least T times T plus 1. While for the leftmost inequality, what we want to do is, given that given T2 is a solution of G squared, we want to find a solution of size square root of T2 in the original graph G. And this can be done by either assembling the vertex copies that participates in the solution for the squared graph T2, or we just restrict on one copy and take that solution. So we have done the argument for the first step. And for the second step, to show APX hardness, the proof is rather involved. Nevertheless, we will show what problem that we're reducing from. So the problem that we reduce from is the max 3-colorable subgraph problem, where the input is an undirected graph G that is 3-colorable. The goal is to find a 3-coloring of G that maximizes the fraction of properly colored edges. It is shown that it is NP hard to find an approximation where the factor is better than 32 over 33. And we show that if there is a p-test for rooted DAG-NBT, then there is a p-test for max 3-colorable subgraph. With the self-improving reduction by squared graph, we also have the following. Assuming ETH, DAG-NBT does not omit a polynomial time or a quasi-polynomial time sub-polynomial approximation. Finally, we show the fixed parameter tractability result parameterized on the solution size. So the problem of interest is the k-binary tree problem, where the input is a directed graph in an integer k. The goal is to answer yes if the graph contains a binary tree of size k, and answer no otherwise. We show the main theorem of an existence of the randomized algorithm for k-binary tree with one-sided arrow, where the running time is 2 to the k times poly n. The tool that we use here is to construct a binary tree in terms of multivariate polynomials. Let f be a field, then a degree d polynomial over the field can be written in this form. The summation of monomials where the coefficient belongs to the field and the degree of the monomial is at most d. We say that a monomial P is multilinear if the variable of this monomial appears at most once. For example, let's consider the following polynomial. In this polynomial, the monomial x1 squared is not a multilinear term because x1 appears twice. In this polynomial, there are two multilinear terms, x1, x2, and x1, x2, x3. A polynomial can be represented by an arithmetic circuit consist of multiplicative and additive gates. And we say that the size of the circuit C is the number of gates used in circuit. In the previous example, the polynomial can be written as a product of sums, and there can be other expressions. And by expanding the expression, we say that the final sum of product expansion is the sum of all the monomials. So a middle step of our algorithm is to consider the multilinear detection problem. The input is a homogeneous polynomial, f, and the goal is to answer yes if f contains a multilinear term, and answer no otherwise. So we say that a polynomial is homogeneous if each monomial has the same degree. A polynomial can be represented as an arithmetic circuit of additive and multiplicative gates, and we assume that there are no scalar multiplications. If f is not homogeneous, then what we can do is to introduce some new variables to raise the low degree monomials so that each monomial has the same degree. Our algorithm strongly relies on the following theorem by Ryan Williams back in 2009. In this theorem, we are given a polynomial of degree at most k, represented by an arithmetic circuit of size S of n, with additive gates of unbounded fan-in and multiplicative gates of fan-in2. And we assume that there are no scalar multiplications. Given this input, Ryan Williams showed that there is a randomized algorithm that on every such a polynomial, it runs in time 2 to the k times poly n times Sn, outputs yes with high probability if there's a multilinear term in the sum of product expression, and always output no if there's none of them. So our goal is to reduce the k-binary tree problem to the multilinear detection problem. So given the graph and an integer k, we want to construct a polynomial that satisfies the following properties. First, the polynomial is homogeneous and has degree k. Second, the polynomial can be represented as an arithmetic circuit where the circuit size is of poly n. And third, there is a one-to-one correspondence between the binary trees of size k in the given graph and the multilinear terms in the polynomial that we would like to construct. As a warm-up, let's consider the case-path problem. So to reduce case-path to multilinear detection, where k-path denotes the problem of determining whether a given graph has a path of size k, let's consider the naive construction by summing up the monomials, where each monomial is a product of all the vertices included. So here we can see that this polynomial satisfies property 1 and 3, but not 2, since there can be exponentially many paths. I want to point out that in this expression, we're actually dropping the edge variables because different paths may cover the same set of vertices. Nevertheless, we will still use this expression for simplicity. So how do we satisfy the second property? So it's actually a simple relaxation. Instead of summing over the paths, we sum over the walks. And this the allowance of self-intersection will satisfy the second property. So what we want to do is to generalize this self-intersection idea for trees. How do we do this? Let's consider multi-trees. So a multi-tree is a pair consists of a given tree T and a graph homomorphism. So the graph homomorphism maps the vertices of the given tree to the vertices of the graph G. The homomorphism maps the root of the given tree to the root of a multi-tree. If the given tree is a binary tree, then in the given graph, the multi-tree is also binary. And we can see that if the graph homomorphism is injective, then we can find a copy of the given tree in the graph G. By following this idea, we can define a polynomial based on the multi-trees and the multi-trees of size k. And we can see that the first and the third properties are satisfied, while the second property can be satisfied by a dynamic programming procedure. So to construct a polynomial of a graph, let's first construct the polynomial of a vertex. So here, a polynomial of a vertex captures all the possible multi-trees rooted at the vertex v, and the multi-trees is of size k. So for the base case, let's suppose the multi-tree only has one vertex v. Then the polynomial will be xv. If the in degree of v is 0, then we can just raise the polynomial so that the polynomial is of degree k. In other cases, the polynomial pkv captures the multi-trees rooted at v of size k, so xv must be included as the root. And there are two possible cases. First, the multi-tree rooted at v has only one child. And second, there may be two subtrees. So in the first case, let's consider the polynomial that captures the multi-trees rooted at u of size k minus 1. And we just sum them up. For the second case, we consider the two subtrees rooted at u1 and u2. And we just sum up all such combinations. And we can see that from this dp, the corresponding arithmetic circuit is of size poly n. Let me summarize and list the open problems. The main takeaway of this talk is twofold. First, the hardness result, and second, a fixed parameter tractability result. On the hardness side, assuming P is not NP, we show that there is no polynomial time constant factor approximations for DAG MBT and undirected MBT. Assuming ETH, there is no quasi-polynomial time sub-polynomial approximation for DAG MBT and undirected MBT. So this leads to an open problem of whether the approximation ratio can be raised in terms of hardness. On the fixed parameter tractability side, we show that there is a 2 to the k polytime randomized algorithm with one-sided arrow for a k-binary tree. And an open problem will be, is it possible to improve the dependency on k? So I'll end my talk here. Thanks for your attention.